Hi everyone. We're going to continue our look at simple linear regression, SLR, and the price odometer application. In this video, we're going to continue to look at the linear regression guidelines, in particular guideline 3 and 4. Guideline 3 states, is the response variable linearly related to the predictor variable? Use a 5% level significance, which implies it's a hypothesis test. Guideline 4 is using the simple linear regression option, identify the least squares of a regression equation, and then interpret the slope and intercept estimates. So to start off, we'll look at question 3. Is the response linear related to the predictor variable? So before you can say how things are related, it's helpful to say, well, what does it mean to not be related? So if things are not related, that means that you have a situation like this. So being related means if you know something about the predictor, you can say something else. You can have a better chance to predict the response. Notice when you have a situation like this is a scatter plot where the correlation is probably about 0. There is no trend line. The trend line is flat. All right, which means the trend line would have a slope of 0. If the trend line is flat, that says knowing something about the predictor doesn't make you any better able to predict the response. So continuing with our data, what we had was we were looking at data. We had price data and odometer data. The question was, it's bivariate data because on each car we're collecting its price, essentially its value, and the odometer reading. The goal of the regression is to predict the price given the odometer reading of a vehicle. The predictor then is the X variables, the odometer reading. What you're trying to predict is the response, and that's your vehicle price. In our last video, we examined a scatter plot, and visually it says, we thought, okay, it looks like there is a negative relationship between odometer reading and slope. It looks like this is as your odometer reading increases, your vehicle price rather decreases. The question is this slope, so the slope of this trend line, is that slope significantly different? Is it not equal to 0? Or would a more proper slope for a problem like this look like something like this? Would this be a more proper slope for the trend line? It certainly doesn't look like it, but that's what the statistics are going to tell us. Okay, so being a hypothesis test and knowing that this is about the slope, our null hypothesis is that there's no relationship between price and odometer reading for all vehicles. Notice in this test, by the way, I use the expression big B. There's big B and little b. Big B is the relationship, or the slope of the relationship between all vehicles. It's the population slope. So our null hypothesis is if we had all vehicles price and odometer, that slope relating those variables, is 0. HA is that there is a linear relationship between price and odometer. That means the slope is non-zero. As a hypothesis test, we have a decision rule. That decision rule is reject H0 if the p-value is less than whatever our alpha level is. Our test statistic, and there I'm going to draw a parallel to something we've done earlier, many things we've done earlier. When we tested means, for example, we had x bar, which is the sample mean, minus mu naught, which is what we thought the mean was under the null hypothesis, over, we'll say S over the square root of n if it was a t-test. And S over the square root of n is considered the standard error of your x bar, of your estimate. So in this case, we're examining a slope. So the t, it is a t-test. The estimate of the population slope is our sample slope, B1, minus what we think the slope is under the null hypothesis, which is 0, over the standard error of B1. We're not going to calculate this by hand. We're going to allow StatCrunch to do the heavy lifting for us. That simplifies to B1 over the standard error of B1. It is a t-statistic, has a n minus 2 degrees of freedom. All right, so the way you get this information is you have to go to StatCrunch, and under StatCrunch I've got the data pulled up. It's under Stat, and it's a regression statistic. Oops, sorry, excuse me. Stat, regression. Okay, I'm going to use my hands for this one, sorry. There you go. And it is simple linear regression, SLR. The X variable, remember, is the odometer reading. The Y variable is the price. And then we're going to simply compute. And notice that what you have is you have this output, and that's what we're going to talk about in the next few slides. What does this output tell us? Okay, so returning to the problem, I copied the first table that's relevant to our output. Here it is. And it gives us what are called the parameter estimates. All right, remember this test is about the slope. And is the slope 0 or is it not 0? And that's the way StatCrunch's default is set up. Is the alternative the slope 0 versus the slope is not 0? The slope coefficient is right here. This is your sample slope, B1. This is the standard error of your sample slope of your B1. When you divide those, B1 divided by standard error, you get negative 13. And think of that as a z-score. This sample slope is about 13 standard deviations less than what we think it is. That p-value is very low. It's less than 0.0001. So we have a conclusion to the test. Since that p-value is less than 0.0001, which is less than 0.05, say 0.05 was our level of significance, we reject H0. Then, in the context of the problem, what can we state? We can state that, so we conclude that there is a significant linear relationship between price and odometer reading for all vehicles. In this test, remember to give me, like all hypothesis tests, give me all of the information, the HOHA, decision rule test statistic, and then give me a good conclusion based off of the table of the information you get from StatCrunch. Okay, the second question is, once we have decided, which we have, that there is a relationship between these the predictor and response variables, we're going to use linear regression to identify the regression equation, and then we're going to interpret the slope and the intercept of that equation. Returning to StatCrunch, the tables, again, we just look at one table. What we're going to do now is in StatCrunch, the information we want is in this regression output. So I've copied the relevant part of the regression output. It's the simple linear regression results. And notice in StatCrunch, if you toggle, you get the data with the regression equation with the fitted line. So output and line, you can toggle back and forth. And here I've got both of them on this slide. So the regression equation in this is hold on a sec, right here. Okay, so the price, which was our Y variable, equals 17.248727 minus this value, 0.06686 and change, times, this is a times right here, odometer reading. That's the regression equation. We've identified it in the output. All right, if you want to, you can write that as, remember we're predicting our price, so that would be Y hat. I'll just rewrite the equation, rounding a little bit, equals 17.24872 minus 0.06686x, where x, Y hat is the predicted vehicle price. And remember, this price is in thousands of dollars. Got to keep track of your units. X is the odometer reading, and the odometer readings are in thousands of miles. So it's important to think about the unit. So there's the equation. Now all we have to do is identify those, or not identify, interpret those two parameters, the slope and the intercept. So in this equation, remember this is actually from algebra 1. Most people write an equation as y equals mx plus b. Statisticians, for some reason, write it as y equals b plus mx. They just commute the mx and the b. So this is my b term. That's my y-intercept. And a y-intercept is the place, it's the value of y when the equation equals, essentially the x variable equals 0. So our x variable is odometer reading, and so the interpretation, what does the y-intercept mean? It means that a vehicle with an odometer reading of 0, that's our x equals 0, has a predicted price of that y-intercept, 17.24873. Okay, but remember that's in thousands of dollars. So a vehicle with a price of 0, or excuse me, with an odometer reading of 0 miles, has a predicted price of $17,248.73 from this model. Note that I state if this is appropriate, and what if appropriate means is if the data are around 0. Now notice this data only goes down to about 20. 0, I would have to continue, would be down here. It really is not appropriate to interpret the intercept because I don't have any data close to 0. Most of these cars have at least 20,000 miles. Lastly, what does the slope mean? The slope in this equation is right here. It's the m part. And that slope is negative 0.06686. I'll round. Remember, that's in thousands of miles. So remember that slope is equal to the change in the y variable, which is the change, delta, change in the price, over the change in the x variable, which is the odometer reading. What we have is that slope is negative 0.06686. And I'm going to write that as a fraction because my slope change in y over change in x is a fraction. And now we have the interpretation. Remember, this is the odometer readings are in thousands of miles. The price is in thousands of dollars. So for if the odometer reading changes by 1, if for every additional 1,000 miles that the vehicle is driven, the price decreases because the slope is negative by 0.06686. But remember, that's in thousands of dollars. So you multiply that by 1,000, $66.86. So for every additional $1,000 that you drive the vehicle, at least with these data, the vehicle price decreases by $66.86.